All right, folks. It's about time to get started for the day. Nice to see everybody. I'm glad that I haven't managed to scare everybody in this class away yet, but we'll keep working on that. A few announcements before we get started here. So let's see. Hopefully you guys all remember the moving parts in this course, but just so that I literally have it on tape that I have reminded you, a few things that are coming down the pike. Your first homework assignment has been posted. It's due, I guess, what, next Wednesday? Moreover, remember that this quiz has these weekly little mini quizzes. This course has these weekly mini quizzes. The first one will go out, I think tomorrow was the plan? Or tonight, even better. Yeah. So there's a 48-hour window to take it. As long as you have watched the lectures in this course and paged through the textbook, you'll be fine. It's just three, four multiple choice questions. Like, they're not intended, like if you're doing a bunch of calculations on a piece of paper, something has gone wrong. Like, this is a question you should just read and think about an answer. Related to that, every year there's some students in the class with accommodations. It's completely fine. So far I've only received one, which statistically is unlikely in a course this size. So if you have not submitted whatever materials you need to MIT, the process changed a little bit. It now goes through the central office and then gets sent to the faculty. Be sure to do that so that we can give you extended time, whatever you need for your exam. Really, it's no problem at all. These are things we can keep track of and do. So that's everything on my list. Any questions about administrative stuff before we get started? Going once, going twice. Cool. Again, I think this class, like, from an administrative perspective, I think this is a pretty straightforward, standard class. Like, we got homeworks, we got quizzes, we got, exams. If you take my graduate class, like a year from now, that gets a little more complicated because there's projects. Okay, so, right. In our last lecture, we were talking about Gaussian elimination, solving linear systems of equations, and all that good stuff, dredging up all of your worst memories from undergrad linear algebra class. And in fact, just to make it worse, I got a calculation completely wrong on the board. And the good news is that it is correct in the textbook. I went back and double checked. It's really just, I don't know. I managed to not only row reduce incorrectly in class, but also in my notes. It's shocking how bad your instructor is at arithmetic. In fact, those who were in my office hours yesterday, A, thank you for keeping me company, and B, I'm sorry that I also got arithmetic wrong in that discussion. So at least I'm consistent. If that discussion lost you, A, that is understandable and expected, and B, I would strongly encourage you to go through the example in the textbook, which essentially just goes through solving this system of equations for x, y, and z. It's nothing special. I mean, it's something you've probably done a million times by now. But the idea is that, of course, I've strategically kind of set up that calculation in a way that parallels the algorithm that we're covering. So if anything feels abstract in today's lecture, you should remember it's really just codifying the steps that you guys have been doing for a long time to solve linear system of equation in an algorithmic fashion. Okay? And in particular, as you might recall fondly from the lecture that, of course, contained no mistakes whatsoever, essentially, in order to solve this system of equations, we basically used three different operations. Right? Or at least, again, in a universe where I solved this system of equations correctly, we would have used three different operations to go from essentially this form on the board to the one that's like x equals something, y equals something, z equals something. And those operations are enumerated on the bottom of this slide, right? We can permute the rows of our system of equations, which of course corresponds to just like swapping the ordering of these expressions on the left-hand side. We can also permute the columns, by the way, but then it's kind of like relabeling the variables. You have to be a little careful when you do that. You can rescale the rows, and we can do this funny operation called forward or backward substitution, where you kind of take one of these expressions, scale it by a constant, and then add it to another one, usually to try and annihilate some variable, right? And so essentially what we're going to do today is show that these steps, A, can be codified into a really nice algorithm for solving linear systems, so you never have to do it again by hand. I promised Hamid yesterday that he'd never have to do this again. And then beyond that, we're going to also show that if we factor this algorithm correctly, or rather if we kind of parenthesize it the right way and think about it, it actually reveals that we can do a really cool thing to matrices, which is to factor them in a form that's amenable to solving linear systems really efficiently. Okay, so the basic big idea that I started to hint at in our previous lecture is that every single step of solving a linear system of equations corresponds to taking that linear system of equations and pre-multiplying it by a carefully designed matrix. Okay, and typically we call these things like elimination matrices is a typical piece of terminology, right? So if you recall from the sort of basic linear algebra thing, sort of the mnemonic that we often use is we set up our system like that. We set up this augmented thing, which of course is really just a placeholder for like AX equals B. This vertical line is sort of doing a lot of heavy lifting here. Okay, and as we apply different operations, essentially we take this matrix and we pre-multiply it by something, right? So eventually we follow all of these steps. We end up with identity matrix and then some other thing, hopefully A inverse B, if we did our steps right. By the way, just because I got it wrong doesn't mean you get 2 on your exam. I'm sorry. It's the irony of grad school. Okay, but in any event, when we do that, what we're doing is we're taking this AX equals B, and I'm going to add some space like that, and we're just kind of like putting matrices in front of it. So like, for example, if we permute the rows of the system, in effect, we are pre-multiplying by our permutation matrix. Then maybe we rescale. So we stick another matrix here, and so on, until eventually what we get on the left-hand side is the identity, which is what we want, right? And so this is just a way to reinterpret the steps that you guys have already been doing forever in solving linear systems of equation. Okay, so today what we're going to do is dig through those steps even more and see that it leads us to this beautiful factorization of a matrix called LU. This is probably the first kind of new thing that you'll see in this course, depending on your linear algebra class in undergrad. And our focus here is algorithmic rather than just existence. Okay, so to go into a little bit more detail, of course, it's useful to characterize the different kinds of matrices E that we can have here. And in particular, what I want you to keep in mind is that each of the individual elimination matrices that we'll work with is easy to invert. When I say easy to invert, I mean there's just like a formula for the inverse, right? There's not a formula, well, there kind of is a formula for the inverse of a matrix A, but it's not a very nice one. There is going to be a formula for the inverse of every one of our elimination matrices, okay? So in particular, when we swap rows, this corresponds to the permutation matrix P sigma. Remember, each of these rows is just like a bunch of zeros and then a 1 corresponding to the ordering of our variables. Does anybody remember the inverse of a permutation matrix? Yeah. It's another permutation matrix. Let's be more specific. Yeah. It's its transpose, right? So P is a good example of an orthogonal matrix. The way to think about it is that, like, if you permute one way by going from I to sigma of I, when you permute, right, you're like kind of swapping the indices. So in some sense, it's just reordering in the other direction. I think is a totally reasonable way to think about that identity. But the basic point is that if one of our elimination matrices E is a permutation, we know how to invert it, right? And we can do it pretty quickly. Okay, next. We might scale all the rows of our system of equation. Anybody want to take a stab at the inverse of the scaling? Yes. That's right. So that's maybe a fancy way of saying that the inverse of this matrix here is just the diagonal of 1 over all these values. That's absolutely right. Okay, and then finally, we had this kind of funky matrix. I think these first two are things that you encounter in any linear algebra course. The third one is a little bit specific to Gaussian elimination, and it's a thing called elimination matrix. And remember that last time we tried to derive this interesting relationship. We also redid it in my office hours, which is good. If you're not used to thinking about sort of writing code in linear algebra format, you might like double check on paper that this matrix does what you expect, right? Which is as follows. It takes row K, scales it by C, moves it down to row L, and then adds it back to your matrix, right? So that last part makes sense because you see this identity term, right? And so essentially, if we kind of decompose this expression, EK transpose times A is going to be the kth row of A. This thing is going to put it in the lth row and scale by C. Okay? So we talked about that last time. And remember that corresponds in Gaussian elimination to this kind of funky thing that we do when we solve linear systems of equations, where we take one row of our matrix, we scale it by some constant, and then we like add it to another row to try and like cancel out some value. Right? That's where I got things wrong in our last class, because it required multiplication by 3. My bad. Okay, so we've justified that diagonal matrices and permutation matrices have easy inverses. The one last thing we should do is double check that this thing has an easy inverse. By the way, typically we can assume L is not equal to K. Otherwise, this is just a fancy diagonal matrix. What is the inverse of this matrix? We talked about this last time. In particular, if I have I plus C, E, L, E, K, and I invert it, now there are two ways to think about this. I mean, one is to construct this giant matrix and start working out its inverse by hand, that kind of thing. But another is to think kind of spiritually. Yeah? So this thing takes a row of my matrix and adds it to another one. How could I undo that operation? Yeah. Yeah, I could just subtract the same thing, right? So if we translate to the math language, that basically says the inverse of this matrix is just I minus C E L E K. Does that make sense to everybody? Sneaky, huh? So this is all to say that all of the individual matrices in Gaussian elimination in solving linear system of equation admit really easy inverses. And that's going to be really important because we're going to kind of compose them all together to construct the inverse of our matrix. Yes? Almost certainly. Yes?
Can you also, like, thing on the right side, just say in words, like, what that operation is?
Oh, absolutely. This takes row, I mean, you can interpret it exactly the same way. This takes row K, scales it by minus C, and adds it to row L.
So that's like subtracting it off.
Yeah, right? Which is obviously the way we want to undo the adding it. Yeah, great question. Any others? Ah, fabulous question. So far, to construct our matrix, I mean, like, you could imagine a really naive algorithm that, like, actually constructs each of these matrices, maybe even, like, makes an n by n matrix with a bunch of zeros in it. The reality is, no, this is a theoretical perspective on what this is doing. And then what we're going to do is, in reality, we're going to kind of keep track of these in a much more compressed fashion. Yeah. Great question. Yes?
I feel like the Elimination flipped in the inverse. Going back to the original.
Not quite. Yeah. So this one threw me off too. This was one of many typos in my original course notes. This is actually correct. So here's the way to think about it. Let's say that I take row 1 and I add it to row 2, right? Then in order to undo that operation, I take row 1 and I subtract it from row 2. It's not that I take row 2 and subtract it from row 1. Yeah. Easy to get this stuff wrong, as you've seen. These are all great questions. I'm glad to, like, I know it's 11 a.m. This is like might as well be like 4 in the morning for our graduate students. So I'm very glad that you're all thinking critically and kind of questioning all the indices because as you've learned, I get them all wrong. So like that's the right thing to do in this class. Okay. So again, our basic operation here, our basic idea is that we've somehow managed to reduce inverting a matrix to like basically decomposing it into like a product of a bunch of little guys, each of which has very simple structure, right? Which is, by the way, kind of cool. Like, this is a nice observation. Okay. And the one last thing that, speaking of things that everybody gets wrong, remember that the elimination matrices appear in reverse order, right? Because I first multiply by E1 and then E2 and so on. This is just like yet another typical mistake that we tend to make. Okay. So everybody on board with the kind of big picture? Now we're gonna go back through this and see if we can codify it a little. Thumbs up. Thank you. It's good to like have a sign of life, you know? Yeah. Okay. So today we're going to start by talking about this Gaussian elimination algorithm, which is just a codification of the steps we've already done. And we're going to see that it is an algorithm that deterministically solves AX equals B, at least, you know, up to double precision floating point, and does so relatively efficiently and is very simple to code, just a few lines. Now, when I say simple to code, it's a few lines of code to code the sort of like vanilla version. The reality is if you find yourself coding Gaussian elimination at home, something has gone very wrong because software libraries, whether you like Python, MATLAB, whatever, all implement this in blazingly fast fashion on your computer using all kinds of clever hardware tricks and so on. Or like we'll talk about later in this course, if your matrix is structured in different ways, like it's sparse or semi-definite, there are other things you can do. Okay? So this is one of those algorithms that like you should all be aware of so that when the code fails, you know why. But if you're coding it yourself, you better have a very good reason. Okay. Right, so to kind of reiterate our story so far, so what did we do? We started with AX equals B. We start basically pre-multiplying both sides by these elimination matrices until we get I on the left-hand side, which effectively means on the right, we've got A inverse, right? Okay. So let's kind of think through this pictorially. You can see that the slides now are optimized for instructors that are bad at arithmetic. And in particular, we're going to think about it kind of like playing a game of checkers here. So rather than thinking about a matrix with actual numbers in it, because that's hard, and we're going to write code anyway, let's think about a matrix that's just generic. So like a picture like this one, right? So what is Gaussian elimination's goal? Its goal is to apply these different operations in a way where I get identity on the left-hand side. Does that make sense? Hopefully I've repeated it like 85 different ways in a slightly different way each time, and one of those kind of made sense. Okay, fabulous. So if the name of the game here is to get basically ones down the diagonal and zeros below and above, we might try to come up with a series of steps that systematically achieve such a goal. Now, for now, we're going to avoid boundary cases where like a 0 pops up in our matrix and we have to cope with it. For now, we'll just assume our whole matrix is non-zero unless something went wrong or we specifically put a 0 somewhere. Okay? This is, of course, a terrible assumption. But we'll come back and revisit the less generic version of the story later, or more generic, I suppose. So what does Gaussian elimination do? Well, the first step of the Gaussian elimination algorithm is going to be to choose something we'll call a pivot entry of our matrix. And so typically that's the upper left when we start, unless there's a good reason not to. And remember, our goal is to get ones down the diagonal. So does anybody have any idea, like how could I get one step closer to the matrix that I really wanted? Yes, Madeline. That's right. I could pre-multiply, to use our new language, by a diagonal matrix, which is basically has 1 over that value I've circled on the upper left and 1s everywhere else. And then, now I don't know much about my matrix, but I do know one thing, which is that I have replaced this value with a 1. Does that make sense? Now, just foreshadowing something that I can already see the hands coming up. When is one case that I can't do that? When there's a 0, right? So the matrix you should keep in mind that's going to break this algorithm is very simple. It's just 0, 1, 1, 0, which is absolutely invertible and won't work for this case. But for a generic matrix, it will. In fact, if you look at the set of matrices for which this algorithm we're describing doesn't work, it is measure 0 in the space of all matrices if you want to be unnecessarily fancy as a mathematician. Yes? For now, I guess generically the pivot element is we're going to rescale to be 1. In the first step of our algorithm, that is the upper left. Good question. But in general, the term pivot here it corresponds to the thing that we're about to rescale to be 1. Great question. Okay, so remember, we're in this like search and destroy mission to get rid of all unknown entries in our matrix. So now I claim we can get rid of the whole first column of this matrix. We can make it exactly what we want using an operation called forward substitution, right? Where, what can I do? Well, now that I have this 1 here, I can subtract off some multiple of that 1 to get rid of this second x, the third x, and the fourth x, and so on, right? By basically just subtracting off exactly, -1 times whatever that value is, right? And when I do that, I end up with a matrix whose structure I know a little bit more about, right? I got zeros all below that 1. And this is by applying a sequence of matrices of this form. And in particular, let's think for a second, what is going to be k in our first step? 0 or 1 because our matrices are 1 indexed in this class. But 0 if you code in any reasonable programming language, other than MATLAB, which is the best programming language. Okay. Don't tell Alan I said that. Okay, right, so now, like, do you see what we're doing here? Like, essentially, we started with a generic matrix, and we're slowly inserting, like, more and more elements that we can be confident are actually the value that we wanted. Now we're going to move our pivot onto the next thing and do exactly the same set of steps to eliminate underneath that one, and so on. And now we have this beautiful matrix here, right? We haven't completely solved our linear system of equation, but we've eliminated everything below the diagonal. This is called upper triangular form for obvious reasons, right? It's a triangle of values above the diagonal. By the way, everybody on their exam, I see at least one exam where the diagonal goes the other way. That's fun, but not super common in linear algebra. Okay, so now what are we going to do? Well, now we have a really convenient situation because this one, if we look above it, right, what can I do? Well, I can cancel out all those x's, and because I have zeros to the left of this one, I can be confident that when I do that, I don't introduce unpredictable values to the left. Does that make sense? So now, whereas I substituted down for the first kind of phase of my algorithm, now I can do the same thing in reverse. I can insert zeros, above the 1 here, proceed backward, and finally, we have reached our beautiful system, which is exactly what we want. So does everybody kind of understand the schematic picture of like sort of our strategy for like hunt and destroy non-zero values and things that aren't equal to 1 and just rescale 1 by 1, right? Notice, by the way, I see your hand, that this algorithm doesn't require pivoting except in very special cases where like you had bad luck and a 0 popped up. Now, what we'll come back to is there might be cases where you want to pivot anyway, like maybe you have a little tiny value in that entry. But that's more of a practical concern. Yes?
So I was just curious, like, as you're going through this, it's very clear that given the size of the matrix, there's like a prescribed number of steps. But like when a person is doing a Gaussian elimination, oftentimes they can find shortcuts.
Oh, that's absolutely right.
So are there ways to like code in like finding shortcuts given a matrix?
Oh, that is a fabulous question. So the question was like, okay, so this is a super generic algorithm. It's very systematic, and we can see that like, you know, as long as you don't have bad luck, this is going to successfully solve your system. But it could be, you're like, when you're doing this in algebra class, I feel like you do it a little more with vibes. Like, oh, there's like, maybe if I kind of reshuffle this way, I can skip a few steps. The question is, can we be systematic about that? And the answer is yes, absolutely. And so in particular, there are certain matrices that are sparse, meaning that there's a lot of entries that are 0. And notice that forward substitution can do an annoying thing, which is take a non-zero value and copy it down into somewhere that used to be 0. And those steps are really bad for Gaussian elimination, right? Because they make your matrix less sparse. And so there are really clever algorithms out there. We happen to have a postdoc in my laboratory who's a world expert on exactly these problems, where you permute the rows and the columns of your matrix first to minimize the number of non-zeros that are introduced during the process of Gaussian elimination. And then you work out the sparsity pattern of the matrix that you'll get kind of step by step of this algorithm, and essentially use a data structure that doesn't store all these 0 values. Codifying that algorithmically is really hard and a topic of modern research. In fact, it's NP hard to do that optimally. Yeah, great question. Any others? I love this stuff. These are super cool problems. This is one of these classes where like we're going to cover a bunch of dumb algorithms you should never code, and then underneath each of those is like a billion cool open research problems that are like right underneath. Okay. So if we go back through our steps and we want to write a piece of pseudocode, it's actually relatively straightforward to do that, right? So essentially when we solve linear system of equation, it kind of happens in 2 phases, right? And this is the algorithm called Gaussian elimination. So first we kind of substitute downward, right? So we go row by row, we scale, so the first element is 1, and then we add multiples of that row underneath to annihilate all the values in the corresponding column, right? And then in the second phase, in backward substitution, we do the same thing in reverse. Okay, so let's put on our undergrad computer science hats for a second. So let's say I have an n by n matrix. How much time does this algorithm take to complete? N cubed, yeah. So let's see if we, it doesn't look like it here because there are kind of only 2 levels to my notation. But of course we have an outer loop from 1 to, oops, m, sorry, my bad. And okay, well what happens in each of these outer loops? Well, we forward substitute down, so that's going to incur another factor of m. Then there's the third one, which is you have to move all the way across the row as you do each of those forward substitutions. Okay? So overall, the runtime of this algorithm is going to be big O of n cubed. You can tell it's important because I made it really big and because I got the letter wrong. That's my bad. But for now, our matrices are square, so n's equal to m anyway. Okay? All right, so, and to go back to the question we had on the front row, of course, the question is this optimal? And we actually haven't proven that. We've just shown that this is n algorithm for inverting a matrix. But for all we know, there's some blazingly fast algorithm out there that does it even quicker than this. I think the common mythology is, at least for reasonably sized n, the answer is no for a generic matrix. Of course, there's practical stuff and there's theoretical computer science. And actually, I don't know the lower bound for solving linear systems. I mean, like for matrix multiplication, it's like that weird, slightly bigger than n squared number, but it only like kicks in when n is like 10 to the ginormous. So definitely there's a theory versus practice issue here. Okay, so does my algorithm succeed for all matrices? No, right? Because of this particular example here, right, where I get to that pivoting step, I really want a 1 in the upper left, I scale by 1 over that value, and of course now I have infinity, not a number or whatever, and so something goes slightly wrong. And so because of this, we have to do a more kind of sneaky technique called pivoting, which basically involves permuting the rows of the column of the matrix so that this doesn't happen. In fact, there's reasons why you might want to do this even if you don't have a 0 value. So like here, maybe I have numerical epsilon instead of 0. And so our algorithm technically succeeds in like infinite precision arithmetic. But if I divide by some tiny number, then suddenly I have some giant thing, and I'm likely to kill the precision of my matrix, right? Whereas like if I swapped the first 2 rows, you know, then the forward substitution step isn't going to start introducing super inaccurate values everywhere else. That makes sense? Okay. So yes. What was that?
Like if you had the epsilon and took, then you swap the rows.
Yeah.
You know, the epsilon, you multiply by 1 over epsilon.
Be careful. So when you forward substitute, you actually don't multiply by 1 over epsilon. You just multiply by minus epsilon. So that's actually safe. Yeah. Great question. James? Yes. See, you guys come to my office hours. Okay. So what do we do to avoid this? We do a procedure called pivoting, which involves basically permuting the rows or the columns to avoid dividing by small numbers or dividing by 0. There are many variations of pivoting. I think the simplest one to implement in the sort of formality we've built so far is row pivoting, right? Which means that you left multiply by a permutation matrix. Row pivoting actually is going to end up being kind of harder to justify for the LU factorization we'll talk about. You can do it, but it requires a little bit of thinking. Or you can do column pivoting, which basically swaps the columns and corresponds to right multiplying your system by a permutation. Either of those is perfectly fine. There are a lot of different techniques out there for pivoting. Remember that basically the more time you spend searching for a really good pivot, the slower your algorithm is, right? So as always, there's a little bit of numerical efficiency issues out there. So probably the best policy from a numerical perspective would be to find the single largest element in your matrix that hasn't been eliminated yet and pivot the row and the column to put that on the diagonal. But of course, that's like an n-squared search step that you've introduced that you didn't have before. It doesn't affect asymptotically the runtime, but it's still expensive. I think a more common thing to do is to just look in the current row or column and to put the largest value there. Now, a reasonable kind of sanity check question you might ask is if I do that second strategy called partial pivoting, like, is there ever a case where like I have a 0 and I can't replace it? Right, that would be the right question to ask. I see 2 head shakes up and 2 head shakes no. I'm tempted to take a vote, but I know that's just calling out students. Let's think about it for a second. Let's say I do Gaussian elimination, an entire row of my matrix is equal to 0. What does that imply about my matrix? Yeah, it's not invertible, right? So I had no business putting that in my code to begin with, right? So probably in that case, I should just stop the whole procedure and say, sorry, like you gave me a bad problem and shame on you. Yeah, okay. Which is perfectly fine. By the way, a lot of times the state-of-the-art algorithm for asking questions like, is this matrix invertible, is to just start trying to invert it, and if something goes wrong, stop. This is completely fine. Similarly, we'll talk about positive definiteness, and to check if a matrix is positive definite, it turns out the best algorithm is to try to factor it in a way that only works for positive definite matrices, called Cholesky. And in one step of Cholesky, factorization is a square root, and if you ever have a -1, then something went wrong. Okay. Cool, so that actually is perfectly reasonable and fairly efficient and easy to code algorithm for solving linear system of equation. But now let me give you a slightly different use case, which shows up all the frickin' time to give you the technical phrase, which is as follows. I have the same matrix A and a bunch of different right-hand sides. Okay, so like for example, in differential equations, maybe the A is the operator. So think about like, I'm simulating physics, got F equals ma, whatever. So the physics remains the same. What changes is like the loading condition or something like that. Very common situation. Now, currently, what's going to happen? Every time I run Gaussian elimination, well, I have to start this whole process over, and I incur another factor of n cubed. And the question is, can we do a little better than that? And let's make a few interesting observations about this algorithm that hints that we probably can do better. In particular, remember the steps of Gaussian elimination. What do? We kind of like scale by a particular scale value, or we forward substitute, or maybe we permute. And let's say that I'm using it to solve AX equals B. So I've got this augmented matrix here. Think about our choices of all of the elimination matrices, E1 through E whatever. Does the choice of any of these things depend on the elements of B? Think back for a second. I see a bunch of head shakes. No, right? Because remember, like, what do? I look down the diagonal of A, and I scale by 1 over one of those values, right? That would be the scaling step. Or forward substitution, I never get all the way to the last column, right? Because the matrix, when it's augmented like this, is wider than it is tall. Yeah? And so this is kind of this interesting observation. Like, I make all these decisions in Gaussian elimination, like what forward substitution to do, how to permute, and so on. And none of those decisions actually depend on B at all. Okay? And so that actually really suggests to us that for this interesting use case where we solve the same matrix on the left-hand side and a bunch of B's on the right-hand side, that maybe we can do better by kind of remembering the steps that we went through. Does that make sense? That's my basic point, that like essentially there's a lot of redundancy if I just call that Gaussian elimination code for each of these things one by one. And the reality is that maybe we can do a little bit better by caching some of those steps and reusing them. And then from my perspective, that's the best way to think about the first matrix factorization we'll talk about in this class, which is LU. It's just a way to remember the steps of Gaussian elimination. Okay? So, oops, sorry. Spoiler alert. Moreover, we actually have one additional hint that we can do a little bit better. Remember that so far in our argument that the Gaussian elimination took cubic time, right? What were the three sort of factorizations that made the cube? The three factors. I mean, one was this loop over the rows, right? One at a time. One was, let's see, Gaussian elimination, right. One is the fact that you're substituting down, and the other is going across that row, right, and doing the substitution each time. Now let's look at the second stage of Gaussian elimination. Got that face, I like that face. Yeah, somebody was like, oh, right. Let's see if that was actually necessary. In particular, let's say I want to back substitute this one, right? From our argument before, that single back substitution step should take n squared time. Do you see that? Because I have to take this row and scale it and then add it to each of the rows above, right? So you incur one loop over rows and one over columns when I do that. Was that actually necessary just for this last one? I see head shakes. No. Tell me why. Yeah, there's a bunch of zeros to the left of this one. Do I really have to keep multiplying zeros by a constant and adding them to previous row? No, right? So in fact, I can do at least this very last back substitution step in linear time by just looking at these two last columns and not touching anything else. Does that make sense? Okay, but now what do I know? After that back substitution step, I didn't affect the left-hand side of this matrix at all. And now I've got a 1 and a bunch of zeros. So in particular, to the right of this one is now a 0. Does that make sense? So now I can apply exactly the same argument. Do you see that? That now that I've completed one step of back substitution, now I have a 0 on the right-hand side, and I can continue to do back substitution in linear time. So all this is to say, I can at least make the second half of Gaussian elimination faster than the first half. Does that make sense? Isn't that a cool observation? Like essentially, once I get my matrix into triangular form, I'm cooking with gas, as they say. Incidentally, you know that American idiom was like apparently invented by like the gas industry. You should look up the history. It's like really wild. Okay. So here's the good news. If we can just solve triangular system of equation, then we're in good shape. We've somehow done that for the first half of or the second phase of our algorithm, but not the first phase. So we're still in cubic time, but like we're doing a little better, right? And so essentially what LU factorization shows is we can do even better than that. Okay, so that's our observation so far. So let's see if we can kind of expose that structure and start to think a little bit more. In particular, let's say we want to solve AX equals B, but we halt Gaussian elimination after we get to upper triangular form. Does that make sense? I'm using a bunch of fancy math words today. It makes me feel very, very grown up. Okay, so in particular here, because I'm inconsistent with notation, I guess I'm using M's instead of E's, but I've used all these elimination steps. On the left-hand side of my system, because I've halted after that first phase, I now have an upper triangular matrix. On the right-hand side, I have God knows what, doesn't matter. Yeah? So here's what I'm going to do. I'm going to define a matrix U, which is equal to the product of all the eliminations I've done so far times A. Any idea why I call it U? Yeah. It's upper triangular. Yeah? Sneaky. I only asked that because the last time I taught this, I was looking at the video and somehow I missed that fact. And I gave it some other name. Anyway, yeah, so this matrix is called U. So here's a kind of interesting thing that we can do is we say, okay, so we have made a definition, U, which is going to be mk to m1 times A. And this thing is upper triangular, UT for Utah. Okay? Now, if U is equal to this, I can reshuffle this definition ever so slightly, right? I can write A, of course, is going to be equal to nk m1 inverse, like whatever that object is, times U. And essentially, we revealed some factorization of our matrix. So far, we don't know that it's particularly nice, but we know that it's some factorization of some darn thing times an upper triangular matrix. Cool? Okay, let's give this thing a name. Any suggestions? L. Yeah. Huh. You guys are so good at this. Okay. Now, L obviously suggests something about our matrix, which is that it's lower triangular. And notice that the vibes are kind of right with this one, because notice that like in these steps, we're always substituting down, right? So it kind of feels like L should be lower triangular, but we do need to justify that, yeah? Okay, so far we have this factorization here, and if we are so lucky as L to being lower triangular, then we're really in good shape, okay? All right. So why is L triangular? We're going to basically prove existence of LU factorization, and then we're going to talk about the algorithm for actually computing it. Notice that so far our argument is not particularly efficient from like an algorithmic perspective. And basically all we have to do is prove a very simple lemma, which I'm almost certainly going to get wrong, which is as follows. If I have a product of triangular matrices, by the way, you can insert lower or upper here, right? Then the product is itself lower or upper triangular. Now, why do I claim that that's sufficient? So remember, so far we're talking about Gaussian elimination without pivoting. With pivoting, we're in trouble. We got to think about that differently, okay? What are these matrices? Well, they basically take one of two forms, right? The two forms that are on the screen. Either they're diagonal matrices. Diagonal matrices are both upper and lower triangular, fun fact. Yeah? Or they take this particular form. And remember that the elimination matrices that take place in the first half of Gaussian elimination, you're always substituting down. Does that make sense? So what do we know about the relationship between L and K here? Think carefully. Yes? K is less than L. Almost. No, you're right, actually. Yeah, K is less than L. I phrased it the other way in my notes. Yeah. But in particular, sorry, we have a bunch of elimination matrices of the form I plus C, E, L, E, K transpose, and K is less than L, as our colleague suggests, and then I contradicted and quickly walked back. Okay? Notice that this matrix is lower triangular. Do you guys see that? So first of all, we have identity matrix. That is, we all agree, a triangular matrix. Now let's think about this one. This guy has a single non-zero element. And where is that element? Yes. In the bottom triangle. In fact, can we be even more? Well, okay, that's where I'm going with that. But what is the position? K comma L. L comma K. Ah, finally, I can tell you you're wrong. No, yeah, this is a row L and column K. That's right. So basically, this whole matrix just has a bunch of zeros, and like a single one in this one spot. Okay. So we all agree that all of the elimination matrices we have in Gaussian elimination without pivoting in the first phase, all of those are lower triangular, and they all get multiplied together. So all that's left to justify is that the product is itself lower triangular. Make sense? Okay. So we're going to try to prove that fact. Get excited, because this involves indices, which means I'm going to get it wrong. Okay? All right. In my defense, after my disaster in our last lecture, I practiced this at home, which means that, nothing. Like math in front of, well, it used to be 90, now more like 50 students is somehow like a completely different category of math than math at home. Okay, so claim the product of lower triangular matrices is lower triangular. Okay? All right, so I'm going to follow my notes here, which is dangerous since at least in our last lecture my notes were wrong. Okay. if I can find it in my notes. Okay. So, proof. Suppose A and B are lower triangular. Okay? So what does that tell us about A and B? That says that Aij is Bij is 0 so long as, we have to go this way, right? So it's going to be whenever j is bigger than I. Everybody quick in your head, sanity check this inequality in your head because we're all going to get it wrong. Yeah, I see the little finger pointing thing. That's good. The good news in this class is there's no cross products, so you don't have to worry about like right hand versus left hand rule. Like when I teach differential geometry and I watch people taking the exam, there's always the one guy that's doing it with their left hand, and it makes me like very sad. But that doesn't come up in this course. Okay, so right. So what do we want to show? We want to show that when we take the product, it basically also satisfies this condition. Okay. So let's do that. So we're going to define C equals A times B. Okay. Now we're going to look at ij element of C, and we're going to just verify that it's 0 so long as j is bigger than I. Okay? So take, I'm going to write in great detail all the steps that I'm confident in, and then once I start getting, my indices wrong, we're going to do like a ... and then like a 0. Do the frustrating thing that everybody hates that professors do in the classroom. In my defense, it's really hard up here. You'll see someday. Okay. So in particular, what is Cij? Well, let's remember how matrix multiplication works, right? It's kind of like this, or this gesture, right? So you go left to right in the first matrix, top to down on the other. So in particular, this is going to be the sum over k of what? It's going to be Cik. Oh, sorry, I already got it wrong. Aik Bk J. I love teaching this stuff because I see everybody start to make these funny, like, like Harry Potter gestures in the air. This is great. Okay. So here's what we're going to do. Here's our strategy, is that we're going to take all the terms of this sum and just show you that they're all equal to 0. So let's draw a little schematic picture really quick. So we've got a product of two lower triangular matrices, like that, right? And now we're going to go like this way on this guy, and this way on that guy. Yeah? So what happens in our schematic? Well, first, we got a bunch of non-zero values here, but a bunch of 0 values there, right? And then the second one, we've got a bunch of 0 values here and a bunch of non-zeros there. So we just have to divide our sum into 2 halves. Does this strategy make sense? I'm tempted to stop the proof here and tell you it's trivial, but for my own personal development, we're going to finish it. Okay? So let's take this proof, or let's take this expression and actually expand it. So in particular, this is, of course, equal to ai1 b1j plus ... And maybe let's stop our sum at right before j. Okay, so we're going to have a I j minus 1 b j minus 1 j. Okay, and now I have to keep doing, I can't stop the sum there. I got to keep going, right? Plus a I j b, you have to be careful, j plus a I n b n j. I think I got it right. Good so far? Now the question is, did I manage to choose the right index here? Let's see if that's right. So if we go back to our schematic, in the sort of first phase of our sum, which of the two things is going to be 0? If this is A and this is B, and I'm going like down the column, the first terms that'll be 0 are B, right? So let's take a look at, for example, B1j. What do we know? We know that Bij is 0 anytime j is bigger than I. Well, so far we're in good shape, right? By the way, we can assume that I is not equal to j here, right? Because that doesn't matter in the matrix product. Okay. So finally, let's look at this guy. notice kind of by definition here, right? This guy is smaller than that guy, so this is still equal to 0. Yeah? So the first half of our sum is equal to 0. Now let's look at the second half of our sum. But when I say half, I mean it in the spiritual, like surface area on whiteboard fashion. Okay, now, well, we have j is bigger than I, so just by definition here, aij is equal to 0, right? And finally, ain, notice the second index is bigger now in a, right? So in all of these cases, I just get a bunch of zeros. I'm going to talk fast and aggressively before you guys notice whatever indexing mistake I probably made. And at the end of the day, I get 0. Cool? Like the proof here is pretty straightforward. It really is as simple as the picture that we drew. Okay? So now we put a check mark because my undergrad introduction to proofs professor told me that you should not put a victory mark at the end of your proofs. Okay. But I have tenure, so I can do that. Okay. So hopefully we've proven our little lemma. And as a byproduct of that, what have we shown? We have shown that so long as we can invert a matrix without using any pivoting steps, I'm going to keep repeating that, our matrix admits a really nice factorization, A equals LU. Okay? Watching the clock. Oh no, I'm late. That's okay. We're always late. Okay. So in particular,
Do pivoting steps correspond to permutation? Like, are those the same?
that's exactly right. Yeah. So we basically noticed our argument really depended on every matrix here being lower triangular, and permutation matrices are not lower triangular. Okay. So in this case, we have LU, right? So let's say that I want to solve AX equals B, which of course is now the same as LUX equals B, which means that X is equal to, careful now. I see like all little finger testers again. Maybe somebody new. Or the same guy, that's cool too. U inverse L inverse B, right? So in particular, how would I implement this in code? I would not compute the inverse of U and L and store them in memory, right? This is just shorthand for first solve this linear system and then solve this linear system. And remember, we already justified solving triangular systems takes how much time asymptotically? N squared. Ta-da! Isn't that cool? So once we have LU factorization, we can invert or solve linear systems in quadratic time instead of cubic. Now, there's no free lunch. How much time do you think it takes to actually get the LU factorization? Yeah, cubic time. That's right. Like, which makes sense because essentially we're going to get the LU factorization by just running through the steps of Gaussian elimination and storing them, right? Like, this is not a super complicated method. Okay. So this is what we just did. So essentially, if we solve a system using LU factorization, we actually solve 2 systems. But the good news is 2 is a much better factor than n. And now we have an efficient way to invert. OK. Incidentally, fun fact, there's actually, like L and U are 2 different matrices. But if you're really sneaky, you can store them both in one matrix because they're triangular. And you can always rescale so that the diagonal of one of the 2 is equal to 1. So if you do that, you can do this nice compressed format. As a gotcha, does it make sense to multiply a vector by this matrix? Absolutely not, right? This is actually just 2 matrices stored in one grid of numbers. Yeah. OK. Right. So we're actually going to skip over the steps of the algorithm for computing the LU factorization because it really is just a reshuffling of Gaussian elimination. As you've seen, I'm very likely to get indices wrong, so I will refer you to the textbook. But like essentially, it's basically what we've already seen. It's just Gaussian elimination, but every time you do forward or backward substitution, you kind of keep track of that number in L or U, depending on what step you're in. Okay? So I'll let you guys take a look at the book for that thing. Now, quick question. How many of us think that every matrix A admits a factorization LU? You might notice I've repeated this many times. Yeah, like the kind of thing you might see on an exam or homework. Yeah, so how many of us vote yes? I give you an A, it admits an LU. How many of us vote no? How many of us, I see you in the back, are like, hell no, Justin is asking a question. I will look straight at my laptop. Like, this is not, I will not participate. Shockingly, there are no hands. Somehow it doesn't add up to n. OK, so you guys are absolutely right. As I've already mentioned, If we have a pivoting step, we no longer can write this factorization. So like if you call LU factorization code in that somebody else has written, chances are it will not output LU. It'll output something sort of closely related. Remember, there's this pivoting idea. So for example, let's say that I pivot columns rather than rows. This is the sort of cleanest version to derive given the proof we have so far. Because remember that pivoting columns is like post-multiplying by a permutation. So in that case, if we go back to our proof from before, now it's almost the same, right? That we have a bunch of elimination matrices, we have A, and now we've multiplied by a bunch of permutations, right? So now I can do exactly the same argument I had before. I get L times U times the big product of permutation matrices, which is itself a permutation. So this sort of justifies an LUP factorization. Cool? If I do row pivoting, I'll get PLU, but it actually requires a pretty yucky adjustment of the proof that we just did to justify that that happens. You have to kind of commute the permutation with your forward substitution, which is like indexing hell. In fact, if you do full pivoting, then kind of unsurprisingly, you get PLUQ. The good news, how much time does it take to invert a permutation matrix? Kind of depends how you store it, right? Like the inverse is the transpose. So if you stored it as a big grid of numbers, then like you just transpose and multiply. But you can do even better than that because really you just store a list of the non-zero values and apply a permutation, which is linear time. Okay. Yes. Another permutation. So this one permutes the rows and the columns because you're doing like full pivoting, right? So you need one that moves things up and then another that moves it to the left. Yeah. Okay, so congratulations, everybody. You are now initiated to the Numerical Linear Algebra fan club. You have your first matrix factorization. Numerical linear algebra is all about factoring matrices like 1,000 different ways. Here's our first. In fact, I guess our first 4. And there will be many more, so get psyched. Yeah, but the thing that I think, the really big theme that I want you guys to get out of this discussion is A, LU factorization is not like some magic thing that like the theory gods pulled out of the air and is like, you know, some fun theoretical fact. All it's doing is basically just caching the steps of Gaussian elimination you've all done by hand a million times. That's all it is. Okay? And similarly, as we look at each of our matrix factorizations in this class, we'll see each one of them basically corresponds to some annoying calculation you did by hand in undergrad linear algebra, right? So soon we'll talk about QR factorization, which is going to be kind of like orthogonalizing a set of vectors, which is also a thing that's annoying you do by hand a million times in linear algebra class, okay? I guess the difference there is that actually the algorithms we use for QR typically are not, what do you call that thing you do in linear algebra class? Gram-Schmidt, because that turns out to be kind of numerically yucky. Okay. So that concludes this little segment of this course. You might notice that the slides for this class are basically divided into a bunch of lectures that don't divide evenly into the lectures of this class. And moreover, I'm bad at time management. So what we're going to do is I've just glued them together into one long slide deck. And we'll just go from one to the next. And I watch the clock and stop at 25. Okay? But the good news is I've taught this more than once, so I know like roughly where we should be at any given point. Okay, so far in this class, what have we done? We've talked about some low-level numerical stuff, and moreover, I've given you an algorithm for solving an actual numerical problem like ax equals b. And I think it's useful to pause here and discuss like why do we actually care about linear systems of equations? I mean, you've probably seen some in linear algebra, but I feel like they tend to be kind of made-up problems, like a lot of like, you know, I can buy 10 apples and I can buy 15 potatoes and they cost this many dollars. You know, like those kinds of problems. But the reality is that linear system equations in computer science are everywhere. And not just like substeps of other algorithms, like just having a piece of Gaussian elimination code around helps you solve all kinds of cool applied problems. So what we're going to do now is talk about some of those, drawn from computer graphics, machine learning, whatever. And then what we're going to do is we're going to step back 10 feet and look at the A and the B, right? We're trying to solve AX equals B. And we're going to see that A has really nice structure in a lot of these problems. And to go back to the question that we had earlier in lecture, you know, like, is this the best you can do? One thing we might do is say, well, I don't need to solve AX equals B for all problems. I only need to solve AX equals B for problems that come out of my machine learning application, right? And maybe in that situation, I know a little bit more about A, and I'm going to be able to formulate a faster algorithm or a more numerically stable one, right? Anybody have an idea of what the most famous example of such a structured problem would be? Rhymes with Meest hairs? Somebody new, please? Anybody? Least squares, thank you so much. Pull me out of my misery here. That's right. And so what we're going to show is that least squares problems lead to linear algebra, lead to linear solves. You can absolutely solve them with Gaussian elimination. The only problem is that that's actually numerically unstable. It leads to squaring the condition number of the problem, which is not so great. And that's what's going to lead us into QR factorization and many other things. Okay, in fact, your homework kind of has you work through a special case. Incidentally, my feedback from Madeline and other people who were kind enough to hang out in my office hours is that the homework, I think as an overreaction to last year, we removed a lot of the formal problems in the first homework and made them more kind of vibes-based, like what might make this code fall apart? And then you guys are now concerned about like, how do I write a proof of this? It's okay, like just high-level description is fine. Yeah. Okay. So, unfortunately, I've done a really bad thing pedagogically here, which is we started with the algorithm and now we're going to end with the application. Right? There's some famous quote from Feynman, who is a terrible human, at least according to his autobiography, that like this is the wrong way to teach. You should lead with the problem and show that your algorithm is the natural solution. We'll do that with the rest of this course, but with linear systems specifically, I feel like we've all seen them so many times we can just start there. But now, let's solve this kind of funny theoretist dilemma and ask, like, what are different places we might actually solve linear systems? And my basic point for today and part of next lecture is going to be that linear systems of equations are insanely important for like 1,000 different reasons. They show up in a lot of applications. Moreover, solving AX equals B will be a sub-step in about 82% of the other algorithms that we talk about in this class, right? Okay. So let's start easy. Let's talk about linear regression. Sorry, in machine learning, we probably have some other name for this. We're fitting a linear model to our data, big data. So right, so let's say that I want to fit a function f of x, has a bunch of different variables that go into f of x, and I'm trying to predict some value. So maybe I'm trying to predict the height of my plant after 10 days of growing it as a function of how much water I put on the plant and how much sunlight it gets and its proximity to Alice's office. So there's some positive correlation, some negative. Regina tells me this is a terrible example because it's like actually famously nonlinear. Especially when it comes to proximity to my graduate students. But in any event, what is our basic task here? We're given a bunch of data points, and we'd like to recover the coefficients A so that f of x fits in my data as well as possible. This is the canonical example of a linear system of equations. Okay? So how might we do that? I give you a data set of xy pairs, right? So I grow a bunch of plants. For each one, I do a controlled experiment. I put some amount of water in. I let it do its thing for 10 days, and I measure the height, right? So the height would be y. X would be all the loading conditions. And I get a bunch of different vectors, x comma y. And for each of those vectors, I plug it in. And what I'd really like is that like y1 is equal to f of x1, y2 is equal to f of x2, and so on. Does everybody understand the notation? Okay. So at the end of the day, we have to be a little bit careful because I think in undergrad or like high school math, we think of like, what is all of math? It's like find x. Is x the unknown in our problem here? No, it's the coefficients a, right? And in particular, if I take all of these relationships, y1, y2, and so on, and I just stack them together, I end up with a linear system of equations. Does everybody see that? So here it's sort of like, x1 dot product with all the coefficients, a1 to an is equal to y1, x2, and so on, right? I see some of you guys making that like same matrix multiply gesture that we're going to make a lot in this class, which is good. So do we all agree that this is just like a cute coat around the previous slide? We just took this set of relationships here. We kind of isolated all the a's in a column vector on the right, put all the x's in row vectors. That's why there's transposes. And this leads to a linear system of equations. Does that make sense? So from our previous lecture, when are linear systems of equations well posed? Like, when do I expect to be able to actually solve this thing for a1 through an? Well, probably when there's exactly n data points. Okay? And in that case, what could I do to recover the a's? I just invert the matrix on the left-hand side, and out comes a solution to my regression problem, and life is good. Okay, so this, and in fact, this this expands to other cases. So let's say that I have an unknown function f, which is a linear combination of f of x's, right? Notice that f doesn't take anything as a parameter other than x, right? So all of the nonlinearity is kind of hiding in the form of f. Then I can still basically do the same argument. Right? So as a famous example of that, let's say that I have a bunch of one-dimensional data, like a bunch of x, y pairs, and I want to fit a polynomial to that data. Then what could I do? Well, let's say that I have a function f of x is equal to a naught plus a1x plus a2x squared and so on, right? So now my data set is a bunch of like x, I, y, I pairs equals 1 to n in this case, or probably, in this case, how many data points do I need to solve this system? Assuming that I do it exactly. To be careful, this is a famous math mistake. Yes? N plus 1. Notice that the a starts with a 0 and goes to n. Yeah. So maybe I do that, right? Now, these are one-dimensional values, but the reality is you get a linear system of equations because, like, let's look at each of these relationships. It's going to say like yi is equal to a0 plus a1 xi plus a2 xi squared, and so on. But remember, the unknown variables are not the x's or the a's, so this relationship is still linear, right? So this is just one simple example of like where linear systems show up in reality. But one thing that we might know from machine learning is that, or from just like common sense, is this a particularly good way to fit a polynomial to data? In general, like if I have some regression problem and I have like exactly 10 parameters in my regression problem, does it make sense to like go out there and collect exactly 10 data points and stop? No, right? In particular, there's like this sort of unnatural byproduct of the math that we've done so far. That like if I want to fit a polynomial or like I don't know, linear function with n inputs, then I can collect exactly n data points and then my science stops, right? And somehow this is like some weird relationship between my experimental procedure and like the mathematical model that I have. And moreover, we've put an exact equal sign here, but we all know that data is really noisy. Yeah? And so somehow we want to address this. You guys can probably guess where I'm going with this, right? And in fact, there's many different names for this. I think in statistics, machine learning, what is this often called? Where I set an equal sign in my regression tool and I go through each of my data points exactly perfectly. Overfitting, that's right. And so in particular, here's, I think, the sort of typical picture that people draw. Like if I have a bunch of data points, maybe these points are pretty well explained by a linear relationship, but because I have forced my model to go through each of these points exactly, I can end up with some really wild wiggly thing, whereas really I should have filtered out noise. Does that make sense? So far, my linear system of equations only know how to overfit. Does that sound so great? And so the question is, how can we use linear algebra but avoid this kind of overfitting situation? And I think there's like a totally reasonable thing we might do, which is just to have more data points than there are unknowns in our problem, like somehow redundancy. But we don't actually have machinery for coping with that yet, so we need to introduce that. Okay? By the way, overfitting is really, really bad with polynomial regression. This is just like a little bit of an aside. Like for whatever reason, if you like overfit a polynomial with like, degree 10 to 10 data points, it becomes really sensitive to the positions of those points. So there are these wild examples out there where you have like points that are basically forming a linear relationship, like a straight line. And then the polynomial that goes through them is like some wild, like, thing like this. But like, so it's very common. Does anybody know for polynomial regression the name of this? Yes. Lagrange interpolation is the algorithm. Does anybody know the name for what goes wrong? We'll talk about Lagrange interpolation, but like 8 weeks from now. This is, I can never pronounce this guy's name. Runge. I always mean to look it up. I think he's German, but he might not be. Runge phenomenon. What this guy said. And essentially, there's like a bunch of math out there that predicts that like polynomial interpolation is really bad above like a certain degree. Okay. So instead of doing that, maybe we relax our assumption that our model goes through all of our points exactly, and that's going to allow us to basically introduce redundancy. Okay, so let's think about how we might do that. Now, here's the kind of fun thing we can do. In linear algebra, we can like reinterpret linear system of equation in like 5 gajillion different ways. There are so many ways to think about the system AX equals B. Yeah? So let me give you yet another one. So let's say that I take my matrix A, and I look at it row by row. So I'm going to label the rows like R1 to Rn, little r1 to little rn, okay? Then notice what happens when I compute the matrix vector product, like A times X. What is the first element of that? Well, it's really the dot product between my unknown X and the first row. Again, remember that gesture. We go left to right, top to bottom. Does that make sense? And so the second matrix vector product is going to be R2 dot X, and so on, right? So from this perspective, we can think of linear systems of equations in a slightly different way, which is to say that, like, essentially, there's some unknown vector value of values X, and I observe its dot product against a bunch of other vectors, R1 to Rn, right? And then I'm trying to figure out, like, well, what is the vector X whose dot product is equal to, B1 when it's dot product with R1, B2, dot product with R2, all the way to the last guy. Does this interpretation make sense? It's like, I think, kind of a nice, like, kind of gamey way to think about it. Gamified? I don't know what that is, but I'm told I'm supposed to do that when I teach. Okay, so, right, so essentially I don't know X, but I do have this like little yardstick that I can measure against X by taking its dot product with a bunch of different R's. And from this perspective, I think it's completely reasonable to just kind of keep doing that, right? Like, just keep adding more and more rows to my system of equation and just keep measuring these different dot products one at a time. From this perspective, maybe now I allow myself to have a little bit of noise every time I make that measurement, but I do it so many times that they become kind of redundant. Does that make sense? So in that sort of pictorial view of the world, essentially, if m is bigger than n, I have more dot products than I can actually solve the linear system with, then the best I could do is ax squiggly equals b, right? I want some x for which ax is roughly equal to b. Maybe if I'm really lucky, they happen to be equal, but I can't guarantee it, because as we know, most of these systems won't be perfectly solvable. So what we're going to do is, the first time we do this in this course, and it's going to be the way we do modeling basically for the rest of this course, because this is a modern numerical methods class, is take almost all numerical problems and pose them as optimization problems. Okay? I think if you go through a numerical analysis textbook from the 1970s, this perspective is a little less common, but these days, this is, I think, is a nice kind of unified way to understand a lot of what numerical methods are doing. Now, what can I do? I don't expect ax to equal b. I can't be so lucky, as we justified at the beginning of, what, 1 or 2 lectures ago. But what I can do is write down an optimization problem. I can say, okay, I can measure this quantity here, right, which is the residual, right? So if I have some x that I'm guessing is like a pretty good solution to this, if I take that norm, right, if I'm so lucky and it equals 0, right, then I solve my system. And if it's small, then I think I've done a pretty good job, right? So I could say, okay, maybe let's see if I can find the x that minimizes this quantity. Okay? So essentially, that is the definition, or one of many definitions, of a really, really important object, which is the solution of the least squares problem. The least squares fit for ax equals b. Now, of course, the terminology here doesn't really align with my notation here. Notice that minimizing a norm is the same as minimizing the norm squared, right, because it's positive. And just from an algebraic perspective, dealing with this thing is going to be easier. Okay? Now, we're all programmed from birth, or like roughly probably, first year of college, to do the following, which is, when presented with an optimization problem, what is the first thing that we should do with this thing? Take its derivative and set it equal to 0, unless you're on or Leticia, and then you take its complex dual. But we'll talk about that in a different lecture. So for now, let's define a function, f of x. And we're going to say that it's the norm of ax minus b squared, like that. Okay? By the way, as a reminder, this subscript 2 here is that the norm we're using is like the square root of the sum of the squares. One might ask, is that the best norm for these problems? Like, might you want to use absolute value? And the answer is yeah, absolutely. It's in certain cases. But the numerical algorithms for solving that problem are a lot harder. So we'll come back to that later. Okay? So, as we said, what should we do? We should take the derivative, set it equal to 0. So let's do that together. Okay, team? So let's actually rewrite f a little bit to make our life a little easier. Now, in general, the norm of a vector squared is the dot product of that vector in itself. Yeah, fun fact. So in particular, in notation that we like in this class, which I want you to get used to, and I want to be your default as you solve homeworks, we can write it this way, right? So if ax minus b is a column vector, if I transpose it, now it's a row vector, and this thing is just fancy notation for dot product, okay? And in particular, what can I do? Well, one thing you might know is the transpose of the sum or difference is the difference of the transposes. Moreover, one more fact you may not remember from linear algebra class, if I take two, like a matrix and a vector, or really two matrices, and I multiply them, and then I take the transpose, that is the same as the product of the transposes in reverse order. Okay? So in particular, this is equal to x transpose A transpose minus B transpose times A x minus B. I promise the math in this class gets harder for the math kids here. Okay. So what should we do? Well, we should, what do they say in algebra class? Like FOIL? Yeah, that's it. Basically, we should expand this product. Okay, and what are we going to get? We're going to get x transpose A x first outer. So I guess x transpose A transpose B. We have to be careful because matrix multiplication is not commutative, so we can't just like glue the middle terms together yet. Minus B transpose AX plus B transpose B. Have I inevitably made a mistake? No? Oh, what a good day. Turns out it, like, actually, you do better when you prepare. Huh. Okay, so we have 4 terms here. The good news is we can actually do 3 terms. Remember that matrix multiplication is commutative, or associative, not commutative. So I can insert parentheses as I need them. In particular, I'm going to parenthesize this way, like that, right? Notice that this thing is the same as A transpose B quantity transpose. Yeah? So these are the same, just like in reverse order. Do you see that? And both of them are just dot products. Do you see that? It's the dot product between X and A transpose B. Okay? Moreover, this is the dot product between B and itself, which is just the norm of B squared. So at the end of the day, I'm going to get X transpose A X minus X transpose A transpose B times 2 plus the norm of B squared, like that. Sorry, I should be careful to keep these subscripts here because when we talk about conditioning, that's going to matter. Okay, so this is a slightly nicer reshaping of our least squares problem. By the way, notice that like this term doesn't affect the least squares problem, right? Because we're going to differentiate. Okay, so now let's take the derivative, or when you're at bar trivia doing multivariable calculus, because our function is of multiple variables, our derivative is a gradient. Now, the textbook goes through a bunch of formulas for gradients of expressions that are of this form in the first chapter. So if you're still getting your matrix calculus brain up and running, that's completely fine. But for now, your instructor will help you out by just giving you the formula. Notice I'm not looking at my notes, which is probably a mistake. But in particular, you'll get 2A transpose A x. And then when you take derivative of a dot product, that one feels right because it's just linear. You're going to get 2A transpose B. Secretly, I know that this is right because I know where we're headed. Oh, no, there's a hand. No. Okay. You know, I have to write some version of this proof basically 6 times a day in my line of work. Okay. So this thing is equal to 0 because we're at the optimum. So in particular, we have derived, fun fact, the world's most famous linear system of equations. Okay? Which is to say, we have shown that A transpose A x is equal to A transpose B. Okay? So what did we just prove? We showed that if you solve the least squares problem, like if your goal is to solve that optimization problem above, that is equivalent to solving a linear system of equations, but that linear system of equations is not AX equals B. It is A transpose AX equals A transpose B. That make sense? Sanity check. This matrix is square, right? Like if A is M by N, A transpose is N by M, then the M's go away. Yeah? Cool. So I have just expanded the toolkit of problems you can solve. Now you can deal with non-square matrices. Okay. So if I want to, I see your hand. If I want to solve a least squares problem, what could I do? Well, at least naively, we'll talk about better algorithms soon. I could form A transpose A, I could compute A transpose B, and now I can put that into my Gaussian elimination code, and life is good. Yes? Yeah, A is not the variable here. X is the variable. That's right. Okay. So this is our system of equations. Anybody have any idea what the name of the system of equations is? Remember this from undergrad? Some of you are nodding, but then you won't help me out. It really kills me. Yes? A little louder for the back of the room. No, like just one more time. Normal equations. Okay, everybody after me on 3. Normal equations. 1, 2, 3. Okay, cool. Anything to wake you up. Moreover, the matrix on the left-hand side is called a gram matrix, which is basically a big matrix of dot products between all the different columns of A. Okay? All right. This is the most famous system of equation. We're going to spend a lot of time studying it. It shows up everywhere. It shows up in data analysis. It shows up in machine learning. It shows up in computer graphics. You want to solve a linear problem? It's probably the normal equation. Okay. What we're going to find in our next lecture is that the matrix of the normal equations is also very nicely structured. Right? Like in particular, one thing you can probably guess is that it is symmetric, right? So already it's a little bit nicer than generic A, and in fact it's also positive definite, which is a property we'll talk a lot about soon. Okay, there are a lot of extensions of this problem. One thing you might do, for example, is regularize your problem, like say like, oh, maybe if I get a vector x with giant elements in it, I know that something has gone wrong in my regression problem. So I add another term to my optimization that just penalizes the norm of x, right? So I add like alpha times the norm of x squared. If I do that, this is called Tikhonov regularization. Essentially, that's going to correspond to adding alpha times the identity matrix to your matrix of your linear system. I'll let you think about that more on your homework assignment. There are also a lot of variations of this story. You might regularize in different fashion. Essentially, the term regularization here just means, on the one hand, I want to fit my data. On the other hand, if I get x with a lot of really weird values in it, like they're really, really big, then maybe something has gone wrong. So now I add some other term that penalizes x's that are really big. That essentially it leads to different optimization problems that are variants of the one that we wrote before. The first one still can be solved with a linear system of equations. If you don't believe me, you should basically go through the proof we just did on your scratch paper with this additional term. These other two we're going to save for later are going to penalize different norms of x, like the L1 norm, which is the sum of the absolute values. This wants x to have exactly 0 values in it. Solving this optimization problem, I encourage you to take the derivative of this with a gradient rather and set it equal to 0. And sadly, like, does anybody know like what is the derivative of absolute value, for example? Think about just in one dimension, right? It like kind of goes down on a straight line and then up. Yeah. Yeah, it's just a step function, right? It's like -1 and then +1, which is like not going to be particularly nice to work with. However, this is a convex optimization problem, so if we have time to talk about algorithms for that, we'll see some techniques for solving in a few weeks. Several weeks, because that's a tricky problem. Okay. There are so many applications, right? So far, the only one we can do in this class is this one. But essentially, there are so many least squares problems in the wild where you take a bunch of expressions that you want to be true of some unknown variable x, you square each of them and you sum them up, and you optimize for x, right? And this is just essentially a good way to get a bunch of things that you want to be true all at once, at least approximately. So for now, we've managed to do this only when fi of x is a linear function. We'll talk later on about an algorithm called Gauss-Newton, which extends our technique here to when the fi's are nonlinear. And it basically does so in a really dumb fashion. Like essentially all you do is take 2 terms of the Taylor series for fi, solve a linear system of equations we wrote down, and iterate. It's really that simple. Okay, so in our next lecture, we'll start off by talking about 2 applications of least squares, just briefly to kind of get your brain thinking about it, because I want you to be able to recognize least squares problems in the wild, even when it's not obvious. And then we'll step back and kind of ask, like, what structure do these problems have in common that's going to allow us to solve them slightly more efficiently than the generic case. Okay, so we'll start next time as a preview by talking about image alignment. So you're given two photographs of the same subject with that are like rotated, translated, squashed, stretched from one another, and your job is to kind of put them both in the same coordinate system, right? And so just to get you thinking about this for our next lecture, I'll give you the problem now, and your goal is to pose it as least squares, which is as follows. I have a bunch of XY pairs, which is like a point in the first image and a point in the second. And I'm looking for the linear map from one into the other that preserves these points as best as possible. So I want a function that kind of looks like ax plus b, where a is like a 2 by 2 matrix and b is 2 by 1. What are the variables in my problem? I've chosen this problem intentionally to keep messing with what letters are. Yeah. Let's try again. Yeah, the unknown here is the transformation, right? It's a and b. It's not the x and the y pairs now. Notice in this problem, a is a matrix, which doesn't feel like it fits into least squares, right? So far we've talked about least squares for vectors. So we'll return to that at the beginning of our next lecture, and then we will introduce you to your second matrix factorization of 6.7350, which is going to be Cholesky factorization, which is basically just LU applied to symmetric positive definite things. Okay, so with that, everybody have a delightful weekend. Do not forget to take your quiz, and I will see you next time. And thank you for that very mild applause. Okay.